for all voltage and all electric field generated inside the material. So coming to the definition again, when a piece of material, either it is conductor or semiconductor, placed in a transverse magnetic field, what will happen? Electric field is generated inside the material. The generated electric field is perpendicular to both magnetic field and flow of charge or current, right? So due to the electric field generated inside the material, what we are observing? So potential difference is creating between the two ends. So voltage is developed across the material. So that developed voltage inside the material is called as a Hull voltage. And this is about Hull effect definition. So coming to the derivation part, we are going to derive the equation for Hull voltage and Hull electric field in terms of magnetic field and current. The PPT I'm going to share now again. Yeah. Is the PPT is visible to everyone? Any one of you please respond. No need to give more messages. Only one student give responsible.
Yes, sir.
Yeah, okay. Are you taking the screenshots, Amma? All effect definition and the derivation part also. To derive the equation for all voltage and all electric field. So I'm going to taking the consideration of forces acting on the electrons. Right? What are the forces acting on the electron? So due to the magnetic field, some force is extracted on the electrons, and due to the electric field also, some force is extracted on the electrons. So I'm taking the two forces, magnetic force B into E into V and electric force E into EH. So at the, under equilibrium position, both are acting opposite directions, right? So at the equilibrium position, the two forces acting on the electrons are equal. So now I'm equating the upward force and downward force, nothing but electric force and force due to the electric field and magnetic field. By equating the two and by taking equation for current density, I'm going to derive the equation for EH equals to J into B by N into E. From that equation, I am taking the equation for RH. What is RH? Hull coefficient. Hull coefficient RH equals to 1 by N into E. So the equation will be EH equals to RH into BJ, and this is the relation between the EH and RH. So RH equals to EH by BJ from that equation only. Now experimental determination of RH. To define the equation or to derive the equation for RH, I am taking the equation for sample thickness and area of the sample also. So by taking the thickness, so I am deriving the equation for EH equals to VH by T. So after that, current density J equals to I by A. So for that, I am taking the area equals to B into T. So when we substitute area equals to B into T, so I am writing the equation for current density J equals to capital I into I divided by B into T by substituting equation 7 and equation 6 in equation 5. This is the equation number 5. Consider equation 5, RH equals to EH by BJ. So by taking the thickness and area, I'm going to write down the equation for EH as well as current density J. So EH equals to VH by T, because of we know the potential V equals to E into D. So here D nothing but thickness of the sample. After that, area equals to breadth into thickness. So current density A equals to I divided by B into T. So by substituting RH equals to EH by BJ in the equation, VH by T and I by B into T, I'm going to find out the equation for BH or VH. Whatever the equation, VH equals to RH into, by rearranging the terms, we are getting the equation for hull voltage developed across the material. VH equals to RH into B into I by small b. So VH is the hull voltage, and try to remember that equation somehow. We have various kind of equations between the relation between the RH and EH, and current density equation, and RH, hull coefficient, and VH also. Previously, in the first slide or second slide, we did the equation for RH into EH. EH equals to RH into B into J, or else RH equals to EH by B into J. Now, in the second relation, equation number 8 or 9 is the relation between the VH and RH. Previously, we derived the relation between the RH and EH, electric field developed across the material. Now, in this slide, we derive the equation for relation between the VH and RH. Try to remember these equations, because of these equations are most important to solve the problems from the module. You know the importance of numericals from each module for your examination purpose. So that's why all of you try to remember the equations, whatever we derived in the Hall effect. These equations are only used to solve the problems from the module. So coming to the application, already I explained about the hull coefficient. What is the use of hull coefficient? By getting hull coefficient is negative and positive, we can identify the material. For determination of type of semiconductor, we are using this Hall effect. How can we identify? By getting the hull coefficient is negative and positive, we can identify the type of material. Already we discussed RH is negative, then the type of material is N-type. RH is positive, the material is P-type material. And to determine the carrier concentration, once we know the RH, so we can easily find out the carrier concentration, or NRP, whatever it is. So RH, using the equation RH equals to 1 by N into E, or RH equals to 1 by P into E. Once we know the hull coefficient, we can find out we determine the carrier concentration. So after finding the RH, using the RH, we can find out the mobility of charge carriers also, mu. So for that, rho equals to N into E into mu, or mu equals to 1 by N into E into rho. 1 by N into E nothing but RH. So once we find out the RH, we can find out the mobility of charge carriers also, where the electrical conductivity, rho is the electrical conductivity. So for measurement of magnetic flux density B also, we can use this Hall effect. And finally, to determine the sign of charge carriers, whether the conductivity is due to electrons or holes. In the same way, similarly, first application and fifth application are similar. We determine the sign of the charge carriers, whether the conductivity is due to electrons or holes. We can determine easily by getting the sign RH equals to minus sign, and a negative or positive. And these are some applications about the Hall effect. So again, to determine the type of semiconductor, once we find out the RH, to find out the carrier concentration also, we are using this Hall effect. Once we know the RH and electrical conductivity, we can find out the mobility of the charge carriers. So once we know mobility and RH and electrical conductivity, we can measure the magnetic flux density and hull voltage also. Okay, these are some applications about the Hall effect. Is it clear, Amma? About the Hall effect, is it clear to everyone? $11:30, 62, 17. So somewhat difficult to understand through online classes, Amma. Try to maximum, Amma. Again, I'm going to share the PPTs of all effect. If you're not taken the screenshot, I'll have to try to take a screenshot. For every slide, I'm going to give 10 seconds of time. This is the first slide. Take the screenshots in order. First slide. Same thing uploaded in the CMS login also, nothing to worry. And coming to the second slide, only diagram. Same diagram. And third slide, for this one also I'm going to give 10 seconds of time. Try to take it. Print screen option. Using the print screen option, I'll have to try to save the slide. The next slide. Sorry. Sorry. Third one and fourth one. This is the fourth one. Determination of hull coefficient RH and hull voltage. So for that, we are taking the consideration of forces acting on the electrons. There are two types of forces are acting. One is electric due to the electric field and due to the magnetic field. Both are acting in opposite directions. So at the equilibrium position, by equating the two, we derive the equation for EH and RH and VH also. So first, by equating the forces, I'm going to derive the relation between the EH and RH. This is the next slide. Try to take a screenshot of this one also. And coming to the next slide. Next slide. Take a screenshot of this one also, Amma. Equation 8 and 9 both are the same equations. So equation 8 for hull coefficient RH and equation 9 for VH. Hull voltage developed across the material. And applications. Sorry. Applications all effect. This is the most important topic, Amma. So one question from A and B. One question is compulsory in your final examination. Either problem or theory. So one question is compulsory having about the Hall effect in your final examination. That's why. And Hall effect also, theory of Hall effect. This is about total Hall effect. Is it clear to everyone? Please respond. If each and every, I want a response from each and every student who are followed that lesson. Please raise your hand. By raising your hand, please Respond. 9 students only responded. 10. Only 10 students. One option is there, Amma, raise the hand. By raising your hand, all of you please respond. 11 only. Make it fast, Amma. Only 13. Okay. 13 students. Very good. Okay, Amma, thank you. So coming to the numerical sum, all of you try to note down the first one. For intrinsic semiconductor, with band gap of Eg, or else we discuss in the next class about the numerical sum. We don't have sufficient time to discuss about the numericals, so we cover the numericals in the next class. Coming to the recalling of N-type and P-type semiconductor. So external semiconductors are two types, one is the N-type and one more is a P-type semiconductor. Coming to the N-type semiconductor, how the N-type semiconductor will be formed by doped with the pentavalent impurities. The fifth electron is loosely bounded. By adding four electrons are doped with the fifth group elements. So 4 electrons are engaged with 4 existing electrons. The fifth electron is loosely bounded, that is free electron. So that free electron we call as a donor electron, ready to donate. So the donor equal to number of donor electrons in the energy level. So these are number of electrons equation. Sorry, sir. And this is the equation gives the number of electrons, and this is a second equation gives the number of ionized donors. By equating the two, I'm going to find out the equation for EF. Where is the equation for EF? And this is the equation for EF. EF equals to EC plus ED by 2 plus KT by 2 log ND divided by 2 into 2 pi ME star KT by square whole power 3 by 2. So by substituting T equals to 0, the Fermi level is exactly between the bottom of the conduction band to the donor energy level. So by substituting the equation for EF here, I'm going to find out the density of electrons in the conduction band for N-type semiconductor or carrier concentration of N-type semiconductor. So that equation we are getting in terms of donor concentration. So that equation is 2 into ND whole power 1 by 2, 2 pi ME star KT by square whole power 3 by 4 exponential of ED minus EC by 2 KT. So in the similar way, we are finding the P-type carrier concentration. Before the holidays, we covered this topic, number of holes in the valency band for P-type semiconductor. So before that, by equating these two, I'm going to derive the equation for EF. So after finding the equation for EF, by substituting EF equation here, I'm finding the number of holes in the valency band for P-type semiconductor. Similar equation, whatever we are getting for N-type semiconductor. This is the equation for N-type semiconductor. Similar equation we are getting. So their instead of donor concentration, their acceptor concentration will present. At the same time, in place of ED, we are getting acceptor energy level. That is the only difference between the equations. So after that, Hall effect. So only the topic remaining from the module 2 is that variation of Fermi energy level for N-type and P-type semiconductor. So all the Fermi energy level equations we are discussed at the low temperatures. Low temperatures. So now we are going to discuss what will happen when the temperature is rises. Fermi energy level, about the Fermi energy level. So what will happen when we rise the temperature or when we increase the temperature, what will happen? So up to now we covered the topics, that is an equation for N. Wait. So equation for N is 4 equations, similar equations. I'm going to write down here 2 pi me star kt. These 4 derivations are also most important. H square whole power 3 by 2 EF minus EC by KT. EF K into T. This is the first equation in a semiconductor. That is the density of electrons in the conduction band. So second equation, number of holes equation. Why I am repeating so many number of times means you know already why I am repeating more number of times. Exponential of EV minus EF by KT. The second equation. So by equating these two, I'm going to find out the intrinsic carrier concentration Ni. You know the equation. So after that, N-type carrier concentration. So for N-type semiconductor, the number of electrons is given by 2 into Nd whole power 1 by 2 2 pi me star kt by h square whole power 3 by 2 exponential of Ed minus Ec by kt. So similar equation for P type. P equals to, in terms of acceptor concentration, we are getting Na whole power 1 by 2 and 2 pi me star kt by h square whole power 3 by 2 and exponential of Ev minus Ea by kt. These are the 4 derivations are very, very important in semiconductors. By equating the two, we are finding the equation for Ni. So for that, we did the equation for EF for N-type semiconductor differently. Here also we did the equation for EF is different in terms of your donor concentration, here acceptor concentration. Acceptor concentration. Here the Fermi level is exactly in between the bottom of the conduction band to the top of the valency band in case of intrinsic semiconductor. These are the topics all of you try to remember. So with the donor concentration and with the acceptor concentration, the Fermi level is different. So that topic we are going to cover in the next class. All right, in the P equals to your MS star, MS star. Not ME star, here MS star. అందుకే మీకు unmute option ఇవ్వద్దురా నాయన మీకు. That's why I'm this allow participants to unmute themselves. I disable పెడతాను. So you are not utilizing properly. when we are when we are given some options to you, you are not going to utilize properly. Please don't do that, Amma. So these are the semiconductor equations. So after that, in the Hall effect, in today's class, Hall effect. So first we are taking the consideration of magnetic field, magnetic force, and electric force into EH. By equating these two and by taking the current density equation J into N into V. So I'm derive the equation for EH. EH equals to Bj by N into E. So here I'm taken RH equals to 1 by N into E. Similar equation I'm writing RH into B into J, where RH equals to 1 by N into E. That is called as a Hull coefficient. This is called as Hull coefficient. Why we are using Hull coefficient? To identify the type of material we are using Hull coefficient. Here. So this is the relation between the RH and BH. RH equals to EH by BJ. First relation. EH by BJ. And remember this RH equation also. RH equals to 1 by N into E. This is the relation between these two quantities. One more quantity we have, that is VH, Hull voltage, developed across the material. Now we need to derive the relation equation for VH in terms of RH. So that is VH equals to RH into the final equation. Derive now. For that we are taking the consideration of thickness T, and area of the sample also. To find out the EH, we are taking into the thickness of the sample. So after that, by taking the current density equation, J equals to I by A. A is the area of the sample. So by substituting J and EH, we are going to derive the equation for VH and RH, relation between the VH and RH. So these relations are most important relations. Try to remember that equations. So first equation RH equals to 1 by N into E, and second equation RH equals to EH by BJ, and third equation VH equals to RH into B into I by T, something thickness we are getting, I think. B. Breadth of the sample or thickness. This is the relation. And first equation for Hull coefficient, and second equation between RH and EH, and third equation between the VH and RH. Fine. VH equals to RH into B into I by B. Wait, Amma. So I hope you understand about the Hall effect. Is it clear, Amma? Up to Hall effect, is it clear to everyone? Because of time is going to running out. Stupid for us. Some students are wantedly going to disturb the class. No problem. So I'm not going to give the option to unmute yourself. If I am given, you are not utilizing properly, right? So that's why I'm not going to give the option unmute themselves. So respond through the chat box. Respond in the chat box. So all effect is clear to everyone. Please respond in the chat box. Make it fast. 56 finally responded. 3 only. Rule number 3. 47, 48, 58, 64, 13. Good, good. Okay. So most of the students are followed. That's good. 33, 50, 53, 29, 51, 6. Okay, Amma. Thank you. Thank you to everyone. 8, 35, 62. In a similar way, attend the classes regularly, Amma. So in the next class, we are going to cover the topics variation of Fermi energy level with temperature and concentration. So after that, we are going to discuss about the numericals from the module 2. Sorry, only the topics remaining from the module 2 are 2 numericals as well as variation of Fermi energy level. So if you are having any doubts, please raise hand. I'm going to give the option to unmute yourself.